Thank you, Chris, and thank you, everybody, for hanging around. I seem to be the final obstacle between a very fine dinner this evening for you and the end of this spring school. When I was asked to come and speak to you, it wasn't quite clear what I should speak on because the whole area of probabilistic numerics has developed at a real pace and developed some real theoretical and methodological depth. And I've just really sat on the sidelines for the past few years, so it wasn't clear to me what I could really contribute. So when I looked at the agenda and it said Speaker Mark Girolami, subject TBC, I thought, well, that gives me some leeway as to what I could actually speak about. So to be confirmed, but I looked at another agenda and it said applications. And so what I thought might be useful for some of you, or at least keep some of you awake for the next 90 minutes or so, is to really motivate the philosophical background of probabilistic numerics, the methodological advances that many of you are making, some of the theoretical analysis that you're seeking to do, and actually show you some real applications that benefit from this completely different way of considering numerical computation. So I'm going to talk about something which we call the statistical finite element method, and in many ways this is a cousin, if you will, of probabilistic numerics, and it really forms the basis of some serious applications, and I'm going to show you some in engineering that are actually out there in the wild that are being used. So if I can convince you that if you look at the statistical construction of the finite element method through PN lenses, and I can convince you that, yeah, okay, this might join the pantheon of PN methods, then when someone criticizes your work, you can say, well, it's having impact in some pretty serious applications. So, what I also thought I would do, because this is a talk that I gave not that long ago, is introduce the notion of digital twins. Digital twinning is one of the buzzwords that are going around at the moment, a bit like AI. But again, there is some real substance in the actual concept of the notion of twinning a real physical or natural system with a digital representation. And I would say that one of the big use cases for the machinery that you're developing in probabilistic numerics can be found in the whole area of digital twinning. So I'm going to give a very brief introduction to what a digital twin is. I'm not going to labor the point because I don't think this is really where your interest lies. But again, it should provide motivation for you when the skeptics and the critics of PN perhaps ask you, what's the point of this? Well, there are real arguments to support the case that something like digital twinning is really crying out for the machinery that you're developing. So I'll just give you a quick whirlwind tour of what digital twinning means and what it doesn't mean. And then I'll lead on to introducing you to the idea of using the finite element method as a numerical scheme, a deterministic numerical scheme for solving quite a large class of partial differential equations. And then pose the question that is quite an uncomfortable one, which is that you have a beautiful partial differential equation or system of differential equations describing a natural or a physical or an engineered system, and you invest an awful lot to solve that in a way that satisfies the various error criteria which I see up on the board there. But the question still remains, is this mathematical, this abstract mathematical description of this reality in the world, is it misspecified? Well, it most certainly is. And in which case, we really need to start to consider the notion of how do we characterize the misspecification in our model. And I would argue that taking a probabilistic approach, so moving away from something that is deterministic based on a truth to something that is misspecified and dealt with in a probabilistic manner. And so I'll do a very simple introduction to the construction of what we refer to as the statistical finite element method. Very briefly look at some of the analysis that has been done in terms of the convergence of this probabilistic method. I'll then look at the methodology that is associated with it. How do we solve the numerical systems? How do we solve for time-evolving systems, for time-evolving nonlinear systems? So I'll introduce some of the methodology, and then I'll show you just some of the examples that have been deployed by people that want to pay money for it, which is always a good thing. And then I'll just introduce some extensions that are currently being considered. And then you can all go for dinner. So what is a digital twin? I mean, what does it mean? Well, in essence, it's a step forward from the sort of classical computational modeling or computational solution of mathematical models that has developed certainly in the last couple of centuries, and certainly in this and in the previous century with the advent of actual digital computation. But a digital twin allows us to combine mechanistic descriptions, and not necessarily mechanistic, or not solely just mechanistic descriptions, of some reality that we can actually observe and therefore gather data from. And so it is basically the combination of a reality, let's just say a physical reality, that can be observed and therefore generates data. And then we have the digital representation, which may well be some computational instantiation of a mathematically abstracted description of the generative reality, and coupling those together in a systematic way that enables us to do more than solve inverse problems, do more than just control, but actually use the physical or the natural reality in terms of observed data to update or to track our actual digital representations, and of course then use the digital representations to monitor, to control the actual reality in the physical world. So we basically have these virtual duplicates of some real system, and the key is that we want to couple our mathematical descriptions to observations from the actual reality. So nothing terribly deep here, but it is something that is transforming certainly the engineering sciences and the engineering disciplines in terms of how artifacts are designed, how they are controlled and operated, how they are managed and monitored. Now, of course, what this means is that we need some knowledge of the underlying mechanisms that describe the systems that we want to twin with. Obviously, we want these digital representations to evolve in time, right? The asset, that's very much an engineering term. If it's a turbine or a generator or an aircraft, that we would be able to capture the evolution of that system throughout its whole life cycle. We would also want to make sure that the digital and the physical, or the real representations, are continuously coupled, so that there is a feed forward and a feedback of data between the two. Now, at present, these representations are artisanal. Right? They are bespoke constructions for each particular asset. Now, I'm using the language of engineering, but we at the Alan Turing Institute are working in partnership with both the Met Office here in the UK and the British Antarctic Survey. The British Antarctic Survey, unsurprisingly, is a British national research institute that surveys the Antarctic. And one of the aspects of the Antarctic that they survey is the polar ice sheet and how it is evolving in time. And of course, this is an indicator of the impact that the changing climate is going to be having on the oceans and in our weather systems. And so we are working with them on developing digital twins of these natural systems, hugely complex, multiple levels of physics, and likewise with the Met Office in terms of predicting weather. So I guess for this audience, one of the things that we want to be able to do is calibrate, well, calibrate's maybe not the right word, but certainly capture and quantify to some degree the uncertainty in whatever it is we are seeking to do with the actual real system. And what digital twinning enables us to do is to quantify those uncertainties using the digital representation, and so that decision-making or policy enactment can be supported not by just a point description of this bridge is going to fall down in 2 years' time, but actually use the semantics of probability and uncertainty to be able to communicate to those that have to make decisions. The application areas are really quite extensive. From health, at Turing, we have a team that are working on cardiac systems. I mentioned the work with the British Antarctic Survey and also with our engineers. There's quite a lot of both basic research, applied research, and then actual spin-out activity to services, as in health services, scientific services, and engineering services. And one of the examples is really quite exciting work that we're doing at the Turing and with many collaborators, hospital collaborators, is actually having a digital twin of cardiac, or the heart of a whole cohort of patients. And of course, statistically, this is very powerful because we can then capture the levels of statistical variability in this cohort of patients that have particular cardiac conditions. But we can also borrow strength from the fact that we are gaining data from each of those at varying rates and so on. I mentioned digital twinning in the environment. There are global activities in building a digital twin of the ocean, and I kind of smile at that because whenever I hear anyone getting really excited about an area of research, we could do this, we could do that, and then we'll do this. I always think you're trying to boil the ocean here. And I think maybe building a digital twin of the ocean is kind of similar in its unrealistic ambition. But nevertheless, I think it's important to have that. Anyway, so lots of global activity, both in Europe and elsewhere, on digital twinning of natural systems. And in the UK, there are a number of investments which are not terribly exciting. But I would say, or I would argue, that one of the main backbones, workhorses, of digital twins would be the way in which we are able to simulate and therefore solve the mathematical abstractions that describe the systems that we are trying to twin. Now, I should also say that, of course, PDEs and the sort of continuum limit representations of systems is but one type of model, or type of representation. There are the discrete, rather than going to the continuum representations, there are the discrete types of representations. Some work that we did with a company on looking at how, when the Elizabeth line in London was being developed, trying to understand how crowds of people would react under certain conditions, so moving in and out of a station, so using agent-based methods. But what I'm focusing on for this talk is the continuum representation, and therefore systems of partial differential equations that require numerical means to solve and to therefore simulate from. And the method that has been developed for almost a century is what is called the finite element method. And I'm a big fan. I think that what has been achieved, both practically but also theoretically, with the finite element method is really quite staggering. So this is a little diagram of all that's required in developing a digital twin representation for a training fighter aircraft. And what you should see right in here is the finite element analysis of the physics that drives the aerodynamics and so on. So that's my justification for alighting on the finite element method. So let me now move on to the finite element method and just give you, I'm sure most of you are familiar with it, probably studied it in Maths 101. There's two Cambridge students, I'm sure you've covered it in the engineering tripos. So I'm going to just recap on it and then provide the motivation for a measure-based construction rather than a function space construction of the FEM. So just to remind you that when we simulate using finite element methods, there are a system of partial differential equations that describe whatever it is we're modeling. And I'll now just focus on physical processes, which are defined in some domain, restricted domain of interest. So, so the PDEs are basically describing some physical laws. Right? So we have physical laws that we understand or we hypothesize, and we represent them in the abstract representation mathematically. And the realization of them is very seldom analytic. It is always going to be numeric. Right? We always have to resort, certainly for anything that's of interest and is not being used to, in a pedagogic manner, to teach undergraduate physicists or engineers or computer scientists. We have to resort to numerical methods, which then requires a computational approach. And so the sort of classical conservation laws, momentum, mass, and so on, give rise to various classes of PDEs that describe natural phenomena in fluid mechanics and so on. But the most popular approach to solving these systems and subsequently simulating them is the finite element method. Now, why is it the most popular? There are a number of reasons. I think there are a number of theoretical reasons because the theory is well-founded. There are a number of very efficient and very effective methodologies in terms of solving FEM. And there's at least half a century of both research standard software implementations and commercial implementations as well. So I think there are a number of reasons for this, but it's pretty indisputable that this is most certainly the most used and adopted approach to solving PDEs. So let me see if I can just do a quick finite element method 101 for you. And we'll start off with the classical Poisson equation, okay, which is basically an elliptic PDE that describes steady state, a number of things, but let's just say steady state temperature distribution within some domain. And for those of you that are familiar with this, you've probably read loads of papers that model oil fields and so on as nice little unit squares like this. Okay, so we have the Poisson equation, which basically is the divergence of the product of this diffusion tensor and a gradient of the function of interest. So this would be temperature, and this itself would be a function of the position or the location in the domain that the partial differential equation has been defined. So we'll call that domain omega, and we'll call the boundary delta omega. So within omega, within this domain, then this divergence of this scaled gradient is equal to some function f. And on the boundary, then, well, whatever the boundary conditions happen to be. But for this example, we're just going to say that the value of the function is just going to be set to 0. Now, the beauty of the finite element method is that these boundaries, these domains, can take any arbitrary shape. That's really important, as you'll see shortly. But for the time being, let's just say we've got a 2D square. We've got this divergence-based elliptic PDE, and we want to solve it. And we have to resort to numerical methods. So we basically want to look for solutions for the function u in some space. So we look at Sobolev space of once differentiable functions. And what you'll see immediately, for those of you that I haven't sent to sleep yet, is that you say, oh, I've got a divergence of the gradient of a function, so this u has to be twice differentiable, so you're looking in the wrong space. Well, this is one of the beauties of the finite element method, is that it lowers the differentiability requirements to aid in the actual search for solutions. So we've got a well-defined space of functions, and there are assumptions that we make on the diffusion tensor. So the diffusion tensor will be in a Lebesgue space with the max or infinity norm. And the right-hand side forcing will just be a Lebesgue squared L2 function. What the finite element method starts off with is it says that we will not look for strong solutions of the PDE. We will look for and we will be satisfied with weak solutions. And it is looking at these, or looking for these weak solutions, which therefore enables us to lessen the requirements in terms of the differentiability of the class of functions, the equivalence class of functions that we want to be looking for. So, the construction follows. We will say that we will introduce another function, an auxiliary function, v, which comes from, well, the same Sobolev space. And we will take realizations of this function and basically multiply both sides of the PDE by v, and then we'll integrate. And some schoolboy and schoolgirl integration by parts leads us to this representation here, right? And so what you can see immediately in the weak form, that all that is appearing now is a first-order derivative of the class of functions that we're going to be searching for. So immediately, the weak form only requires one-time differentiability for the Poisson equation. And so what we can do, this is all just one big linear operation. And so we can write, this is a bilinear form because it's bilinear in both grad u and grad v, just as calligraphic A parameterized by some set of parameters in the diffusion term, and then this inner product on the right-hand side. This is what we take forward in the finite element method, this bilinear form. So what's next? Well, the next thing we do is we now need to define an approximating class of functions. And so we introduce a space, we'll call it calligraphic V sub h, defined over the domain of interest. And what we do is we'll select a set of basis functions, so M basis functions, which will span this space, calligraphic V sub h, where h is basically a parameter which describes the way in which we take the domain omega and basically layer a mesh of finite elements on top of it. So that h is related and describes in summary form the span of the basis functions that we've chosen. Now, we know that V sub h, defined on the domain, is going to be a subset of the space of trial functions, and which of course is equivalent to the space that we believe our unknown function that satisfies the PDE resides. And what we can now do is we can approximate at each point the solution using this finite basis. And of course, this is just going to be a linear combination of the basis functions in the finite trial function space. And what that then means is that this infinite dimensional object here is approximated in finite dimensional form, where if we just plug in this basis expansion into the bilinear form and into the inner product on the right-hand side, we end up with a finite dimensional representation. And what you'll see just shortly is that this is basically just a linear system, an n-dimensional linear system that we need to solve for. And there are lots of approaches to solving those, and I'm sure that you've already had talks on how you can do this in a probabilistic numerical construction. One of the really powerful things about this construction is the analysis, and the error analysis tells us that given the equivalence class, so given the function u and our finite dimensional approximation, UH, then the L2 error norm is going to be bounded by some constant, the norm of the forcing of the elliptic PDE, but by h squared, where h is basically the representation that describes the way the mesh covers our domain. Okay, so h would be some sort of characteristic dimension of the mesh, the finite mesh that we've used to represent our continuous domain. Which means, of course, there's an inherent consistency that as you throw more compute, as you refine the mesh, then the error will decrease as well. So it's always good having a bit of theory, even if it might not actually be much use to you. Helps some of us sleep better at night. So what we end up with is a linear system, where A is typically for linear elliptic systems, and it's called is it the mass matrix? No, it is the mass matrix, yeah. Which is basically constructed of the action of the bilinear form on, so the ijth element of A is just going to be the bilinear form acting on the basis functions, so the ith and the jith basis function. Now, what we've got here is that the physics described in the PDE, and I'm just showing you the Poisson equation, which again is, PDE is 101. I'll go on subsequently to talk about time-evolving nonlinear PDEs. The key here is that the physics that we have distilled and represented in the PDE is now captured in this matrix here, A. So it's a physics-informed linear system. One can consider it as a deterministic system of equations to solve. And there are lots of advanced numerical linear algebraic methods, Krylov methods, multi-grid methods, preconditioning approaches, and of course now probabilistic numerical methods. And I'm hoping someday we'll actually see some numerical analysts and engineers actually using PN methods at this stage of the finite element game. I mentioned that the finite element method does not just stand or fall on domains which are nice and geometrically simple. And here are some examples here. Here's a structural engineering example, highly complex, highly indeterminate system, and yet the stress, strain, deformation profiles can be solved for an incredibly complex structure. In biomechanics, here is a domain, a 3D domain of the lower jaw. Again, we can mesh it and we can solve the governing equations that describe whatever the physics is, so what the forces are on various areas of the actual bone. And then an electrical or electromagnetic application here, so solving electromagnetic field equations in very complex domains, so the stator of some sort of generator. So the FEM method, widely used across many areas of engineering, many areas of physics, biomechanics, the natural sciences, describing atmosphere and so on. Interestingly, finite element method also happens to be the preferred approach in fluid dynamics. So computational fluid dynamics is seen as the poor relation of the finite element method when solving fluid dynamical style problems. Okay, well, that's great, but you're here to think about probabilistic numerics. So here's the rub. We know, or at least I hope you all know by now, and if you don't, you're going to have to wake up pretty soon. But our models, right, are actually just representations of reality which are idealistic. And that means that there is going to be uncertainty associated with that equation, that beautiful equation or system of equations that you can write down. It is just an idealization of some reality. And therefore, there is an uncertainty immediately introduced into our modeling. And that takes us away from the deterministic world to one where we have to introduce the calculus of uncertainty. And you have all been, I'm sure, very philosophical after a few beers in the evening, discussing probabilistic versus deterministic numerical methods and so on. The reality is that we have an uncertainty, and if it's important, we need to not ignore it. So, one way of thinking about the finite element method to deal with uncertainty would just be to say, well, look, we know that there is going to be uncertainty in the fact that the model that we've described is misspecified to some lesser or greater degree. So what we could do is we could say, well, in actual fact, the class of functions that we have are not deterministic, or there is a deterministic component, but there is some stochastic component that describes, or potentially describes, the uncertainty in the model specification. Whether that is structural, whether it's because there is some inherent stochasticity, or whether it's just because there is model error. And it's something like this, and you've all been studying this, that allows us to admit that there's uncertainty and to quantify it and then propagate it in, you know, if we have a modeling right through to decision-making process. But what this also allows us to do is, one, admit that our models are misspecified, or if we want to use cruder language, just wrong, but might be useful. It enables us in a systematic and coherent way to assimilate data into the models. And that is something that weather forecasting does and has been doing for quite some time. It allows us to solve the inverse problem, that diffusion tensor. There are parameters associated with that. Or you know, we might have a stiffness matrix that kind of describes the elasticity or the plasticity in the sort of continuum mechanical descriptions. So we could solve inverse problems. And I'll come on to this at the end, is combining, has anyone mentioned deep learning at all in these talks? Anyway, some sort of nonlinear function approximations within physical systems. So how do we do this for the finite element method? Okay, and everything that I'm putting up here is in its simplest form, just so that you get the ideas. So don't switch off because I'm using a linear model here. In some of the publications that we've had, we are dealing with nonlinear systems, we are dealing with time-evolving nonlinear systems, and so on. So this is really for your benefit, just so that you get the ideas, and then you can critique them and develop them and what have you. So if we go back to that linear elliptic PDE, and what we'll do is we'll actually characterize uncertainty by saying, well, we're going to model some uncertainty by a stochastic forcing. And you've all, I'm sure, had a number of lectures already on linear Gaussian systems and so on. So for the moment, let's just say that the stochastic forcing is a Gaussian process. Now, I don't normally start off with a Gaussian process. I normally present this by constructing a Gaussian measure in the Hilbert space, or the Sobolev space, and use that as a reference measure in that infinite dimensional space. But this is something which you're probably a little bit more familiar with. It's a Gaussian process. We're going to make some assumptions. Let's just assume that the diffusion tensor is there's no parameters. It's all well defined, and it is bounded, or its value is bounded. And what that then means is that the push forward of the Gaussian measure associated with the stochastic Gaussian process, pushed forward to the function u, then induces a Gaussian process on u, which has a mean which corresponds to the operation of the Green's function associated with the linear operator on the mean of the stochastic forcing. And then there is going to be some covariance kernel, which is basically the operation, again, of the Green's functions on the original kernel associated with the covariance operator of the related Gaussian measure. So what this does, now there are two ways to interpret this probabilistically. What we can do is we could say, well, we have this function space and it has this geometry endowed, so it has inner products, it has norms defined, but we want an additional structure in this this function space, and that additional structure is going to be a measure, and in this case, a probability measure. And so what we've basically done is we've expanded the properties of our Sobolev space by defining, although this is defined as a Gaussian process, there is a corresponding Gaussian measure associated with it. And so we therefore have a reference probability measure in this function space. In similar manner to when we work in RD, we would have the natural reference measure in constructing any probabilistic representation would be d-dimensional Lebesgue measure. And for those of you that have taken a course at Cambridge that I teach to fourth-year engineers, you should be able to, in your sleep, show that Lebesgue measure is not defined in a Hilbert space, in an infinite dimensional Hilbert space, but a Gaussian measure is. And so therefore, this provides us with the reference measure to enrich the function space in which we are going to be seeking solutions of our PDE. And so therefore, if we take a statistical approach, we can say, well, we've got a reference measure in an infinite dimensional space, and that therefore enables us to define a likelihood, which is well defined in that infinite dimensional function space. If, on the other hand, you wanted to take a Bayesian perspective, then what we have done is we've defined a prior measure, which enables us then to move, if we have data, move from that prior to a posterior, but do it in a way that is well defined in an infinite dimensional function space. And here's just an example here. So the radon-Nikodym derivative of this Gaussian measure that we've constructed, and this is a measure that is now conditioned on y, which is some data, would of course lead to some density. And if, for example, we had some linear observation operator of the acting on the function that solves for our PDE. So again, a very simple data model here. And again, this is simplistic, but not the end of the story. But it's simplistic enough, again, for you to get the ideas. So we could say that we've got data, which is basically some linear observation operator acting on the function that solves for the PDE, plus some observation noise, which in this case here, we're just assuming is Gaussian. And so this then allows us to construct either one, a well-defined likelihood with respect to a reference measure, which is Gaussian, and which also takes into account all of the physics, and we'll go into this just in a moment, that has been captured in the PDE. Or, if we want to interpret this in a Bayesian perspective, we have a prior on the equivalence class of functions that would satisfy the weak form for the PDE. And once we observe data, we can then transform that to a posterior. And this is really quite powerful. It looks very simple, but this is an incredibly powerful construction in terms of model evaluation, model updating, and so on. So this Rn derivative will define a posterior Gaussian measure on the L2 function space. And I won't belabor the points, but these will be under certain criteria for this potential function phi, will be absolutely continuous with respect to each other. And that turns out to be actually very useful in constructing simulation-based methods where we may well have a grid which has got millions of degrees of freedom. So statistically, we're working in extremely high-dimensional spaces. Okay. One of the things that's important here now is that in the finite element construction, we have our mathematical description, we have our numerical, finite dimensional numerical representation, and then we have a solution. With this construction here, as soon as we observe data, now this is Bayesian Statistics 101, but the implications, practical implications are far-reaching. Because what it means is that we can now assess, we can now test our modeling assumptions. And we can update the mathematical description of the physical system that we are seeking to represent. So, and you'll see some examples just shortly. The question then is, okay, this is all very nice, but is this all consistent? So in other words, as we refine the mesh, will this prior or will this reference measure converge in a consistent way to something that is mathematically sensible? And that's one of the strengths of the finite element method, is that you can answer the question from a function theoretic, or function analytic perspective, is that, in fact, I think someone wrote this, maybe not. The L2 error between UH and U converges at a rate of h squared. So this is great. we know that the more compute we put in, the better our error is when solving for our misspecified model. So what guarantees would we have with this probabilistic measure theoretic construction? I'll maybe just cut to the chase and say that we've got two random fields, U, which is infinite dimensional, UH, which is finite dimensional. They're both defined on the same domain. What we would hope for is that UH will converge to U as H tends to 0. And this turns out to be really important, and I think this is very much in line with the probabilistic numerics philosophy. So unlike the L2 error norm in a functional analytic treatment, we now have these measures. So what would be an appropriate distance or discrepancy to assess how well the measure on the field U and UH are coming together? One of the issues with the analysis is that there's no guarantee that the measure on U and the measure on UH are absolutely continuous with respect to each other. So in other words, they may well be mutually singular, which then precludes a whole load of discrepancies based on any divergence, KL divergence, Hellinger distances, and so on. So the analysis that was done looked at a Wasserstein 2 distance between the measures. And there's a paper in the Siam JIUQ journal, which basically gives a really nice result. It says that the Wasserstein 2 distance between the measures for U and the measures for UH is bounded by some constant and H squared. So this, of course, is exactly what is obtained in the functional analytic classical analysis in the finite element scheme. Now what's interesting is that this paper shows that as the variance of that forcing goes to 0, then these measures will converge to Dirac measures with all the mass centered on basically the solution. Right? So the Green's function acting on F, or the finite dimensional representation acting on F. And so we have this consistency in order H squared. And that seems to please the numerical analysts that have looked at this sort of work. So in terms of moving away from a deterministic functional analytic way of solving numerically these PDEs, we move to a probabilistic construction. We actually see that that construction has the same consistency, right? But we have this additional structure, this additional measure structure on the function space. So this is all good. So we've constructed a probabilistic representation of the finite element method. We've shown the analysis in terms of the convergence of measures, certainly in a Wasserstein 2 distance. And so there's a consistency and a coherence between what has come before and what we have now. So what about the methodology? How do we actually realize this statistical finite element method? Well, I think a lot of the work that you've been hearing and has been presented to you by some of the experts in the audience would certainly provide tools to realize methodologically this statistical finite element method. So if we just look at, go back to the stochastic weak form, and we then project down from the infinite dimensional space onto the space determined by the number of degrees of freedom induced by our mesh, then what we see is that this finite representation, which again is linear, induces this finite dimensional Gaussian law. So the value of the function u at each of the nodal elements, conditioned on whatever parameters are associated with the model, will be a multivariate Gaussian with a mean which is identical to the Krylov solution of the weak form. So this should tell us that we're in pretty safe territory. And then we have this covariance structure here, which is basically induced by the, so this matrix here, G, is basically the covariance structure that's induced by the basis functions that have been chosen to represent the domain. And of course, the mass matrix incorporates all of the mathematical description of whatever the physics it happens to be, or the biology or the chemistry, whatever, that it happens to be describing. So everything we know, everything that we've encoded about the physics in the PDE is now represented in the mean and the covariance of this very simple and very well known, certainly to this audience, structure here. So what this means then is that we can simulate by simulating from this multivariate Gaussian structure. And there's a ton of ways in which you can do that, a ton of ways that you can do it in a PN perspective. And the one that I thought might be interesting to you is one which I'll just describe now. But let's say that we've observed data, right? So we've got some grid, and we've made some, which may not necessarily be aligned to the mesh, and we've made some measurements with statistical error. And again, just for simplicity of representation, we're going to say that the observation operator is just linear. In the further work, we'll be looking at nonlinear and non-defined observation operators. I'll skip over the sort of statistical model of the data generation process, because this is all Gaussian processes 101. But what's really exciting is something that you might not really see at first glance. This second equation here. So this is just conditioning on data. This is just prior to posterior updating, whatever you want to call it. We have our statistical, we've got our probabilistic, finite dimensional Gaussian measure on the class of functions that are consistent with the PDE, the weak form of the PDE. And what the classical finite element method will do is just return the mean of that, and you're done. If we've got data, right, so some data y conditioned on whatever this solution happens to be, and then of course what that means is that now we can update UH, the measure in UH, to a measure in UH conditioned on data. So immediately we have the tools to enable us to assess the misspecification of the model that is describing the data generating process that we have been representing in this numerical form. And there's a whole host of things that we can do. We can look at marginal likelihoods, blah, 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 blah. You're all familiar with that in terms of mesh refinement. So using the standard statistical, using the standard Bayesian calculus, we can now use all of these tools to aid mathematicians or mathematical modelers, engineers, physicists, in actually asking quite deep questions about the assumptions that are inherent in the mathematical descriptions and models that they have been cooking up. So how do we simulate from this? Well, Cholesky decomposition, or many of the methods that have been developed in the PN community. Another approach would be to use standard diffusion style methods, which are very popular at the moment. And so there was a paper on the use of Langevin dynamics in simulating from these statistical finite element methods, again in the SIAM Journal of UQ. And so what's quite interesting about this, and again, it's kind of obvious when you look at it long enough, or you've been working in this area long enough, is that in solving the linear system, that's what you need to do, you need to solve a linear system. But now what we're doing is we're simulating realizations of this function, a finite dimensional representation of this function, u. And again, thanks to Pn, we can now take into account the uncertainty associated with the numerical method. And so the numerical method that we are looking at here is just the solution, or the driving of this this Langevin diffusion here. Driving that numerically does not require the explicit solution or exact solution of the linear system. All we need to do in the evaluation of the gradient of the potential is just the matrix, the mass matrix operations directly. And what that means then is that we can have very crude realizations, but we can characterize the uncertainty in them. So we might not want to, we might not have a computational budget that would allow us to run this for a sufficiently long time to have small error But it doesn't matter. Whatever our computational budget is, we will have a notion of what the uncertainty is going to be. And that can then be communicated. So given this computational budget, here is the level of uncertainty. Can you do anything with that? So this is all detailed in this JIUQ paper. And it was quite interesting. There was analysis showing how the error develops. And again, in using stochastic calculus rather than sort of deterministic functional analytic analysis. And unsurprisingly now, they are both consistent with each other. So the KL divergence between the probability at the kth iteration of the SDE, the discrete representation of it, and the actual asymptotic limit is bounded by, unsurprisingly, the actual step size, order of the step size. So we can control at any k what that divergence would be. So the bias can be made arbitrarily small if we make the step size arbitrarily small. And there was further analysis showing that that divergence is also a function of the condition number of the covariance of the measure, which again is not terribly surprising to probably most of you in here. But it gives us a good sampling methodology to generate realizations of these finite element measures. So that was all useful. What else have we got here? So I can give you some examples. I'm conscious of the time. Yeah, you can read the papers if you're having difficulty sleeping at night. But again, the consistency, if you have a large step size, then you're going to have to live with a large bias, but you then also have an indication of the numerically induced uncertainty in that particular setting. So I'll maybe just rush on. I mentioned that for those of you who think, well, the linear time invariant Poisson equation isn't terribly exciting, I probably agree with you. But we did do work on time-varying nonlinear dynamics, where the equations are basically some time-evolving term, du by dt, and then a linear operator on u, and then a nonlinear operator on u. Again, I won't go through the construction because it's pretty tedious, but there is a PNAS paper which describes that. So that's time-evolving, nonlinear PDEs. And yeah, that's sort of using the sort of state space machinery that one would expect. So I won't go through all of that. There are practical issues in scaling this to very high dimensions. And again, there was a paper in the Journal of Computational Physics that looks at low-rank representations of these statistical finite elements, scale up to large degrees of freedom. But I want to just finish off with some examples. So there is theory. There is novel methodology, and it all looks great, and we can publish papers, and you'll get your PhDs, you'll get postdocs, you'll get tenure positions, you might even get professorships. But what really excites me these days is actually making a real difference, or at least being around when that real difference is realized. And one that I'm really proud of, I've got to say, is this one here. Network Rail in the UK, they operate the whole rail system throughout England, Scotland, Northern Ireland, and Wales. And a few years ago, they commissioned the construction of some new bridges in Staffordshire. And my predecessor at Cambridge, Lord Robert Mayer, he had been a pioneering civil engineer who really believed that civil engineering would be transformed if we could measure, a bit like Lord Kelvin, the great Victorian physicist and engineer. He said, you know, if you cannot measure something, you cannot know it, and you cannot improve it. And so what Robert pioneered was the development of fiber optic methods, right, that could be embedded in large-scale infrastructure to gather data. And that's great. And so these bridges were constructed, and when they were constructed, when the cement was poured, these fiber optic cables were laid, and there was of order of 200 sensors distributed throughout the deck of these bridges. And Network Rail then installed the instrumentation so that there is a continuous feed of data from these bridges. And they said, well, that's great, but what are we doing with this? All this data is, I mean, every time a train goes over it, we're generating gigabytes of data and don't know what to do with it. Because you'll be glad to know that bridges are designed so that nothing much happens to them in about a century. Right? So not a lot of terribly interesting dynamics would be seen, one would hope. And then I came along, realized that there's a great opportunity here to actually build a twinned representation. So by taking an FE model and actually coupling it with the data feeds, right, from the structure itself, meant that with this probabilistic, this statistical construction of the finite element method, we could then use the data to update our misspecified models and also use the most, the simplest model, computationally simplest model that would be representative of what was actually going on the bridge. And likewise, once we have that, we can then play out numerous scenarios for Network Rail, who owned this asset and wanted to monitor it, in terms of, you know, what are the loadings going to be, what happens if we put more traffic on, so playing out what-if scenarios, but also just remotely monitoring this particular structure. And so again, we published this very applied work in a journal recently. Well, actually, yeah, not that long ago. But what's exciting is that this is now being used. Right? The quantification of uncertainty is actually being used, and engineers have come to rely on this digital twin, which has, you know, a probabilistic finite element construction, which is what one of the issues that the engineers had was that the finite element method would say the answer is X. And they would say, well, we know it isn't X. What would it be? And there are lots of hacks, and so clever hacks that could be used. Having something that was that had theory, that had nice methodology, and had the uncertainty that is important to them quantified and being able to be communicated to them so that they can make decisions. We're going to send some technicians out to the bridge, or no, we don't need to, or we need to reduce the loading or daily loading on the structure and so on. So bridges aren't the sexiest things to be working on, but being able to, to really show that the machinery that you develop, the theoretical, the methodological machinery that you're developing, actually has a real role to play in something of real economic value to, certainly to the UK. It's extremely exciting. I won't go over all of the details because I'm running up to time, but you can see the data. I think this was far. I can't remember how many carriages were going over the bridge at any one time. But you can read the paper if you so choose. A little bit of MCMC because that's what we do. But a coherent finite element model of the Staffordshire rail bridge with uncertainty quantification via this actual method that I've just described to you. And there's lots more. The reason that we did this work, so this was actually modeling subsurface waves, which are called solitons, was because Shell, who were operating liquid or natural liquid, Chris, can you remember what? Liquid natural gas refineries offshore of the west coast of Australia. These large, huge ships which had extraction capability to bring the natural gas out, but then all the refining plant was on the ship. And the model was that extraction and refinement took place on this vessel, and then customers would just come and offload the processed natural gas. Solitons, when they develop in certain regions of the ocean, can develop enormous amounts of energy. And if they collide with any subsea structures, potentially can cause real damage. And we were asked to look at ways in which they may well be able to predict the energy levels that are developing in solitons. So we looked at this. There are equations that describe solitons, so the time evolving, non-linear, so this is third order derivatives, spatial derivatives. And the interesting thing was that we looked at, so basically what you can do is you can develop a tank and generate subsurface waves and also measure them using these gauges. Right? So you can measure the heights and get the profiles of the waves. So we've got data, we've got models, but we are statisticians, we are machine learners, we are sensible people, and we do not place unmerited faith in the exactness of this equation, or these equations, to describe this physical phenomenon. And what was really nice about this work is that we could show the way in which the model, right, so the deterministic finite element solution of this time-evolving nonlinear PDE, it would go out of synchronization with the data. Why? Because it's misspecified. If we then updated with the data the finite element solution, then we see that the posterior distribution over the profiles brought them back into synchronization. So the models, the misspecified models, were being updated by the data. And this was really nice. Anyway, lots of other things. I won't go into reaction diffusion and so on. But one final thing. I've suggested that the observation operator for the data is 1 linear and 2 known. In many cases, the observation operator is 1 nonlinear and 2 unknown. And so what can we do? So the sort of examples would be that rather than measuring pressure of waves, we've actually just got a video of the structure of the waves. So what can we do in cases like this? Not wanting to stand on the sidelines of the deep learning party that's going on, but one way of actually representing these sorts of nonlinear and unknown observation operators is to use tools such as encoders and decoders. And we've done some preliminary work on that, and it's still preliminary, shall we say, but quite interesting. So the finite element model is defined in the latent space, and we use the encoders and decoders to do the nonlinear mapping into that space. That's, as I said, early work. So let me, yeah, there's lots of examples. So let me just close by saying that a probabilistic, or if we want to be grand, a measure theoretic, statistical construction of the finite element method enables us to synthesize data with these FEM models. And using, if we want to be Bayesian, posterior updating, or just likelihood-based methods, then it really allows us to, in a rigorous way, use data to assess the veracity of the assumptions that we have made in mapping our, whatever our knowledge is of the physical or the real system to the mathematical description. And it allows us to quantify uncertainty and quantify, to some extent, model, or certainly update, misspecified models. And I think that's probably it. There's a few papers that you could look at. So I'll close there, right on time.
Thanks very much. That was a very inspiring talk and a really great overview of the statistical finite element methods. We are at 5:30, but I think we should take some time now for questions. If we've got questions.
You've all just woken up, so I'm sure it'll take a bit of time to...
Yeah, one question I have is, this is like all about modeling the misspecification between them and your data, right? But there's like quite a lot of like underlying sources of that misspecification. Does it make sense to like put that all together, like discretization error and unknown physics and misspecified parameters?
Sure, and I think for those of you that are looking at probabilistic numerics, there's the numerical compute-constrained uncertainty due to the constraints of compute. of course, that all makes sense, but I would say that it makes sense in situations where it makes sense, and it can be done in a reasonable way. So yes, absolutely. I mean, I think there's a lot of holes in this work, which I'm sure you can fill in.
I have a question about the, first of all, thanks. I have a question about the last application where you essentially try to learn in latent space. So you have video data of some physical process, learn in latent representation. Do you then still impose like the mechanistic model, for example, that describes waves, if you have video of waves, in that latent space? It's not clear to me that you should necessarily learn variables that satisfy that differential.
Yeah, so that, I mean, that's basically what we were trying to do. We were saying that if these are waves, then we believe that these KdV equations are describing something useful, and so it's information that we've got. It's latent information that we've got. So let's use it. As I said, this is very much preliminary work, and it's not clear just what regularizing effect, or the flexibility of the encoders and the decoders. Do they really need this latent, this physics-informed latent representation? I don't know. I mean, we can make good arguments that will get past referees, but the reality is, certainly, I don't know enough about encoders and decoders to understand just how much they can actually model and represent.
Can I ask a quick question? If I were coming from a numerical analysis background, I would know that FEM has some other functionality, so it can give you ways to adaptively refine your mesh. It can provide sort of local and global a posteriori error estimates and so on. Do you think you can get that same functionality in Stat FEM because it's based on the FEM effect?
Yes, and it's just, I think the work that Andrew Dunk, or Yanni and Andrew and John did was the sort of precursor to that more fully developed suite of analysis that could be done. Just needs to be done.
Okay, if there's no further questions, then let's thank Mark once more for his talk.